Okay, in this lecture we're going to be learning...
Yeah, the bell.
God!
Let's go.
Saved by the bell.
In this lecture we're going to be learning about basic gravitation, which is chapter 13. Well, gravitational force is just the fundamental force between all objects. All objects feel gravitation, but they don't necessarily... You can't necessarily see it all the time. Like, really, really small objects have such a small gravitational force that you can't observe it. You mostly see gravitational forces between very large objects, like planets, stars, black holes, galaxies, massive things. Every object has a gravitational force on another object that is equal to the one that object's picking on the first one. So every two objects that have gravitational force on each other have equal forces on each other. So let's say we have a planet here and a planet here. These are both applying the same amount of force on each other. Regardless of how much bigger or how much smaller one is, they're still applying the same force on each other. It's just how the law of gravitation works. Alright, so the most basic equation when it comes to gravitation is Newton's law of gravitation. And this is that gravitational force, Fg, is equal to the gravitational constant, which I'll explain in a minute, times the two masses of the two objects over the radius squared. The gravitational constant is 6.67 times 10 to the negative 11. This is just always true no matter what. Like, throughout the entire universe, this is the universal gravitational constant. No matter what objects you have, it is always being multiplied by this constant g. This big M, the m's are interchangeable really, but the big M is generally used for the mass of the bigger object. Like, if a moon is orbiting the planet, the big M would be the planet, the little m would be the object orbiting it. Those are the two masses. R is just the difference between their centers. So if you have two planets like this, R is this line here, not, say, this line. There's an easy mistake to make in this. So another basic thing to know about gravitation is that gravitational forces add up as vectors in various directions. So if you have, let's say, an object here, and an object here, the gravitational forces from this one, and the gravitational forces on the first object from this object are going to add up, like vectors add up, which is something you learned at the beginning of physics, in that sort of direction. Just like adding up regular vectors, you calculate the force of gravity on this one. Let's call this body 1, body 2, body 3. So the force between 1 and 2 plus the force between 1 and 3. Add them up just like you would any other vector, and you would get the total gravitational force on this object. It would be feeling a pull in this direction because of the two objects here and here, slingshotting it this way. An important thing to know in working with gravitational forces is that since radius on the denominator is squared, it has a lot more of an effect on the gravitational force than, say, the masses do. If you have two objects that are extremely massive but really, really far apart, the force can still be negligible. And if you have two really, really, really small objects but extremely close together, you could still have a very large gravitational force just because of that radius. So to find the gravitational acceleration of an object, you take a very familiar equation, which you should probably know by now, F equals ma. Replace the force with the gravitational force, and the acceleration with the gravitational acceleration. Plug everything in.
Which way does air push something as false? Which way is air going to push?
These little m's cross off because this mass here is the same as that mass of the smaller object in that gravitational system. You have left the gravitational acceleration, that's an A, ignore my handwriting, is equal to g big M over r squared. So to find the acceleration due to gravity, the mass of the smaller object, just like on any other situation on Earth or anywhere, it does not matter. This is only if a planet is not rotating. This is just if a simple planet staying in place, pursuing the acceleration of another object moving towards it, or any sort of object, not necessarily a planet, anything. This is just
Remember, and I talked, this is.
simple gravitational acceleration.
This is
How-
like a kick is like a continuous
However,
flow.
to find the gravitational acceleration of a rotating planet or object, which we're going to call G star, that gravitational acceleration, first see this free body diagram. Let's say we have a person standing here. Hey Bob. We have the normal force acting up on them, the gravitational force acting down on them, but we also have the centripetal force of the moving planet drawing down on them. So, when you put that in equation form, it ends up giving you this. You have gravitational force minus the normal force is equal to a centripetal force. So you have, plug in the various constants for each. You're going to be very familiar with that G of M over R squared. Normal force is just mg in this case. Mg star, that's important, is equal to m omega squared r. So if you want to solve for g star, to find the gravitational acceleration on that planet, on that rotating planet, you, first of all, the little m's cross off, which is something you see a lot in this. Isolate the g star, so you have
Okay. What forces are acting on the chair? What else? Okay. Is there anything else?
that would have been nice to
Air
mention.
acting over.
Okay, so
One time air.
I believe this up. The end is still there.
The only way that air counts.
I knew I made a mistake somewhere.
is moving.
So yeah, you're left with gravitational acceleration on a rotating planet is equal to gm over r squared minus omega squared r of that planet at that point. So when it comes to gravitational forces on the inside of a planet, this probably sounds really weird, but it's actually not. You just got to think about it. So you have a planet here, and say you had a hole drilled through the middle. Let's assume it's not rotating. That would mess up a lot of things. Makes life very difficult for us. Just not do that. If you're going to move, make it horizontal for the sake of the graph. If you were to move from the inside of the planet outward in this direction, your gravitational forces, make a little graph here, would look a little something like this. It moves up in a linear fashion as you start to move out towards the edge of the planet, and then once you leave, it drops off exponentially until you get away from the planet and it approaches zero the farther away you get. When you're inside the planet, at the very center, the gravitation from the rest of the planet is pulling equally on you outward in all directions. So at the dead center of the planet, gravitational force on you is actually zero. At the dead center, you'd just be floating around because the rest of the planet is pulling you up equally in all directions. It would be very strange. Didn't really go into that and turn it to the center of the Earth. Move farther out, the gravitational force increases because in planets, it's on the inside, is what the gravitational effects has on you. Only what's on the inside of that radius you are currently at has any effect on you. The rest of this has no forces on him right now. Alright, so now we're going to do some practice problems. Kept thinking about this.
Okay. This is the Earth. Some of you might have been there. This is the Moon. They're a distance r apart. Okay? So now we want to figure out the attraction between the Earth and the Moon. So, the equation for attraction between two objects is G m1 m2 over the distance squared. Right? And that is the force. So we want to find the force between the two objects. Alright? We're going to call the Earth big M, and the moon is going to be little m. So to do this, we plug in constant g. So the force is going to be E. 6.67 times 10 to the negative 11. That's g times the mass of the Earth, which is 5.9 times 10 to the 24th. Times the mass of the moon, which is 7.36 times 10 to the 22nd. All divided by the distance squared, and the distance between the Earth and the moon is 3.82 times 10 to the 8th meters. Alright, so we plug all that into a calculator, which you're probably not doing right now. And it comes out to the force is going to be 2.01 times 10 to the 20th newtons. Alright, and I'm back. So now, we have the sun and the earth here, okay? And we know that the gravitational attraction between them is g, mass of the sun, mass of the earth, over the distance squared, right? So from there, if the sun became a black hole, besides it being really cold and really dark here, we'd be fine. Because g, mass of the sun, does not change. It just condenses into a smaller area. Mass of the earth doesn't change. R squared doesn't change. Therefore, it's the same as if it were still the sun.
Am I in? Alright, well that's all for today. Good luck and happy physicsing. You're gonna need it.
Bye.
This is for stationary. Right.
If the rate, what?
Remember, this is for stationary,
What do you mean for stationary?
because if it starts spinning, it changes.
Oh.
So